functions become just a product, the product, the characteristic function.
And that's why it's
of the
useful.
sum becomes a product of the characteristic function, so that's why
But in Moyar's original paper, you will not find the hidden potent coming out.
I'm sorry, Bess, but why? Where is there's no psi on the left hand side of the equation? There's one on the right hand side.
Which, this equation?
Yeah. Where's the psi?
Psi star, psi.
No, he means on the left hand side.
But on the left hand side.
Here?
Yeah.
Well, because I've gone to, look, I've used a shorthand notation. Let me,
bracket notation from physicists.
yeah, it's a shorthand notation.
But
Put psi, put it in here to begin with. Psi of x and psi. Eh? Put the psi in there right away if you don't mind what I've done.
Yeah, yeah.
The trouble with trying to present something so there's not too much formulae on the slide is...
Yeah.
No, it's just do the integral with psi star x there and psi x there, and it works. You can see how it's going to work out. You've got the operators here.
Yeah.
You've got a vacuum expectation, so you can turn to. You can use the Bargman transformation to go from P, x and P to A and P. A dagger.
Mm.
And it's.
So you kicked out the Heisenberg algebra?
Sorry?
You kicked out the Heisenberg algebra and the Schrödinger representation. Now it comes back in.
Yes.
Sneaks back in.
Yes. Yes. I haven't got the Schrödinger equation at all. I'll get the Schrödinger equation if you give me patience.
I will be patient.
Okay? I'm just, for Morris's benefit, here is the quasi-probability distribution that's used in Wigner-Moyar theory. Okay? So I plugged in from this rather general set of assumptions. And I'm now deriving the Moyar. In fact, I'm going to derive the Moyar algebra. Oh, this is just, why is it called for I was going to say for people like George, but he's going to get cross with me. Why is it a quasi-probability distribution? Well, because you can work out all the expectation values of quantum mechanics, treating it as if it is a probability distribution, classical probability distribution. Quasi, unfortunately, it becomes negative.
This is one of the main properties in Weil calculus.
Yes.
Of course.
Yeah, of course. I mean, but you see, I'm putting it in, look. By emphasising the idempotent. I'm putting it in right from the beginning. Okay, so that then ties in with what you're doing, Morris. Oh, I noticed a sudden change. No, it doesn't matter. What is this? Oh, I've just added this. Notice. Quantum Liouville plus von Neumann idempotent is Wigner-Moyar.
So, do you amplify this?
Well, this is summarising what I've already just done.
Yes, so this is what I'm trying to see.
Well, I start with the Liouville equation, okay? And now I've got it in a strange way, but whether you agree with the way I've got it or not is entirely a different issue.
Where did you get it? Because I didn't know.
I got it from the unfolding infolding.
Oh, yes. Okay.
Yeah?
But where does it play a role over here? Because we can all do all of this without the Liouville equation, can't we?
No, but the Liouville equation, the idea is process is folding, enfolding, unfolding, enfolding. So either you didn't believe or just switched off when I was talking about that, saying this guy's crazy.
No, I didn't. I tried to follow.
No, well, it's... No, I was going the wrong way now. Where was it? Here. I'm sorry, maybe this put you off.
No. So
it's this equation.
No, this I understood.
Okay, but this is, now I'm saying that becomes, I'm now going to call that the Liouville equation, even though I'm not using it in the sense of physicists.
No, that's fine.
Okay, so what's the problem?
So, but this did not play a role yet in what you did just now with the Moyar representation, but this is going to come.
Yes, it did.
Where did it?
Oh no, it's going to come. No, you're quite right. I'm sorry, it's my fault.
Okay.
It's my fault. Wait a minute.
No, okay. No, I just wondered if I was...
No, I haven't. I'm sorry, yes, you're quite right. I haven't... Well, this is for something to keep in mind. Sorry, I've something... Right, sorry, I was misinformed you there. You're quite right. What I need to do now is to try to derive the time dependence for this. So I need to know the time dependence of the... Here we are. Now I'm going to say, all right, now I want to use this. Thank you. With this idempotent. So I then do the, look what I'm doing, I'm finding the standard way of doing the expectation value. So here, this is this equation written out with the h as h and the m as, there might be a sign wrong there, excuse me if there is. The m is that m there. Have I got a sign wrong? I think I have one there. I don't know, anyway. Forget this about the sign. And then I've got the dm by dt, where the m is the expectation value of that. And now if I write the Hamiltonian as this w, which is the var symbol for h, and then put it into this equation here and do some work, which is only integrating and maybe differentiating a couple of times or something, you know, standard. I then arrive at this expression, which then Royale shows, again by just cleaning it, it's a mess. 2 pages of foolscap to get it out. You arrive at the Royale bracket. So you're coming from this idea of the unfolding, you've got these 2 equations, and if you treat these as idempotents, and in particular you take that idempotent, you derive the Royale algebra.
You can go the other way around also.
Of course, but traditionally we go the other way around. But what I'm really saying is, are we doing it wrong when we go the other way around? Because I never understood how you do it the other way around. And you've got, by the way, I've smuggled in a deformation parameter here, but that was to, I had an exponential which didn't show up on here, h tau, exponential I h tau. And if I take h as energy and tau as time, then I've got to make it dimensionless, so that's just action, so I've got to divide by some parameter. And the parameter I'm choosing is h bar because that's what we do, but it's nothing to do with quantum mechanics yet, it's just a parameter, it's a deformation parameter. Okay, so we've got the Royale bracket, and then Royale shows that you start from the Royale bracket, and you then get the standard distribution, time development equation for the quasi-probability density, with this ugly thing on one side. And this comes back again. When you actually look at that, it's like saying that in order to compare 2 points on a trajectory, you have to bring in this sort of non-local integral. This is an integral here. It's bringing in information about the p-states over a whole distribution. So you're sort of building in this folding, unfolding without actually realizing it. And when you go to the classical limit, it just becomes that equation. And that's just a point substitution.